couple weird things about it. The leading edge, or the first part going through its orbit, is blacker than a parking lot, whereas the following edge is beautifully white. So this moon is tidally locked to Saturn. That means the same face always faces Saturn. So that means that the leading edge is always the same. And it's thought that it has been slamming through some carbon-rich dust thrown off by Saturn's some of the other outer moons. When they would be hit by meteors, the dust would fly off, would slowly kind of migrate into Saturn, and this moon was picking it up, and which made the leading edge so dark. It also has a weird feature. This, you can see here, it's a raised equatorial mountain range. So this range here is higher than Mount Everest, and it runs perfectly around Iapetus's equator. And we have no explanation for it right now. It's heavily cratered, so we know it's very ancient. And there are at least 4 current hypotheses about it, but none that completely explain it. And any new hypothesis or theory must explain all previous observations. So we have no idea how it got to be this walnut-shaped moon. The next one is also a moon of Saturn. Now it has a diameter just under 400 kilometers. So this is the smallest astronomical body that we know of that can still be round because of its self-gravitation. And that kind of works usually for most things about 500 kilometers, but Mimas is probably mostly ice. So it only needs about 400 kilometers of that ice to self-gravitate into a sphere. Its most distinctive feature is this huge, giant crater on it. It's 130 kilometers across, and the impact that made this must have nearly shattered Mimas. It's barely holding on. Hold on. No problem. Okay, where are we? Mimas. And it seems to be most well known now for its resemblance to the Death Star.
Wow.
Staying at Saturn, Saturn's hexagon. So it has this beautiful, perfect hexagon cloud pattern around the North Pole. The sides here are 14,500 kilometers long. So that the Earth is smaller diameter than that. And it's a bit more than 29,000 kilometers across, and maybe as high as 300 kilometers. It might be made of a jet stream made of atmospheric gases. So we have jet streams on the Earth. This might be a jet stream on Saturn, going about 320 kilometers an hour. It was first discovered on the Voyager missions in 1981 and was later revisited by the Cassini missions in 2006. Now, during the Cassini mission, when it was photographing this from 2012 to 2016, the hexagon actually changed color from this mostly blue color you see here to a more golden color. And that's possibly due to seasonal change. Saturn sometimes, just like the Earth, it sometimes the North Pole is facing closer to, or facing the sun a little bit more, and sometimes it's pointed away. The South Pole does not have this kind of hexagon. It's got some storms, but none of this hexagon. The hexagon rotates every 10 hours and 39 minutes, which is the same period as Saturn's magnetic field. So it is assumed that somehow the magnetic field is making this, or at least contributing to this structure. Now, hexagons are not rare in nature. Nature loves hexagons. We see them in honeycombs, soap bubbles, volcanic columns. When lava cools, it can make these hexagonal columns. Insect eyes, turtle shells, naturally occurring crystals, and snowflakes. The hexagon is a shape that fills a plane with equal size units and leaving no wasted space. And it minimizes the perimeter for any given area. So it's a very efficient way of packing things together, and nature just loves using it. Here we have Io. It is a moon of Jupiter, and it kind of resembles a pizza. Its surface is remade more quickly than any other object that we've seen, mostly due to volcanically violent place anywhere that we know of. There's at least 100 active volcanoes on Io, and at least half of them are erupting at any one time. It's nearly our moon's twin. It's just 5%, so a little bit larger than our moon. But our moon is gray and colorless and unchanging in its appearance, where Io's surface mutates between yellows and oranges and reds. And most of this is sulfur in various stages of solidification. And the source for all this subsurface heating, which allow these volcanoes to erupt, is because Jupiter is really close by and Io has an elliptical orbit. It's not perfectly round. So we can see here that it's a bad illustration, but it's the best one I could find, that Io is being stretched and both ways. And if you took some Play-Doh and kind of kept stretching it, you'd feel it actually warm up. So that's heating Io, the interior of Io, and allowing these volcanoes to erupt. Its most violent eruptions can throw these huge umbrella-shaped plumes around each volcano. A single explosion would create kind of red rings, and then as the sulfur cools down, it will go to that yellow-green, and a cold white sulfur dioxide frost appears nearly everywhere else. So now, what are some of the weird things in our Milky Way galaxy? These are planetary nebula. In 1786, William Herschel found a small blue-green blob up in Draco the Dragon, and it had the color and size of Uranus, which he had just discovered 5 years earlier. So he noted in his book that it looked kind of like a planet, and that name stuck. So now these are called planetary nebulas. It has nothing to do with actual planets. It was about 80 years later that William Huggins examined it using his spectroscope. Remember, we talked about spectroscopy last week and how by gathering the light and breaking it into its color, its spectrum, we can see those lines that tell us what these things are made about. And he found that it's exclusively glowing gas, so absolutely no resemblance to a planet. And the sky is filled with these things. They are expanding gassy blobs, many of them kind of round like this. And most of them we can see the central star in them. In all of these cases, this was a sun-like star that has completed its red giant phase. So it's used up all the energy in the center and it's expanded. And then as it gets to that red giant stage, it starts puffing off the outer layers. And while that happens, the inner core is shrinking down to about the size of the Earth, becoming what's called a white dwarf. And this material will remain visible for about 10 to 50,000 years before it's spread out so much that it becomes invisible. And we have about 5,000 have been cataloged in our galaxy. These are some of the things that I really like looking for with my telescope. But not all planetary nebula are the same, of course, because it's very dependent on the area of space that they are. So here we have the Cat's Eye Nebula. And this is the one that William Herschel first found in Draco. Of course, he didn't see it anything like that. It was just this little glowing glob to him. And we can see that some odd things have happened as it's been puffing off its outer layers. And we can see these very evenly spaced rings all around it. And if we take a bigger look, oh, actually, we can also see it's got some bipolar jets forming here and some very intricate gas explosions in the center. Now, this is just the very central part of the nebula. So if we back off a bit, we can see the nebula actually looks like this. So this whole part is contained in this little area there. We can see that it had some very, very ancient explosions. Well, shouldn't call them explosions. A long time ago, other gases have puffed off, making this very complex planetary nebula.
Is this something that that you would be able to see with your eye looking through a telescope, or would this be like infrared or some other wavelength?
These were probably long exposure Hubble pictures. You can see, I've seen it through my telescope, but it just appears as kind of a little bluish blob. So very tiny. You certainly don't see any of this detail. And one of the weirdest ones that we have in our galaxy is called the Red Rectangle Nebula. It's located in Monoceros, the unicorn. It's about 2,300 light years away. Now, in 1915, a binary star was found here, but it wasn't until 1973 when the object was studied in infrared that it showed this dust, really odd dust cloud that surrounds it. Now, other than we've seen kind of straight lines in that hexagon of Saturn, but really straight lines are almost non-existent in the universe. And here we see this enormous gaseous nebula that is shaped like a rectangle with these very straight lines through it. Its color is also weird. Now there is some glowing hydrogen, which usually shows as red, but this red-orange color has been determined that it's dust being lit by ultraviolet light. And this dust will made of complex carbon-rich molecules. But so we can understand the color, but what about its shape? The overall formation could result when spherical gas ejections, so coming off the star at all points, disruptive extra material every few hundred years. So there could be some interstellar material around the star, and those explosions of gas are running into it. But that doesn't really doesn't really explain everything either. And these intermittent ladder structures could be where eruptions deposited extra material every few hundred years for whatever reason. They're just not found in any other nebula that we can see, these very straight kind of ladder-like things. So I said it was a binary star. Now these stars orbit each other every 319 days, and they're one is a normal star, normal hot star. The other is a red giant. So this normal star is pulling off material, and they have a very eccentric orbit. So they don't orbit each other nice circles. It's very elongated with how they orbit each other. And when they're close, there might be extra material being pulled off because of the increased gravity. And then when they're farther away, less material. So that might be one cause of these intermittent ladder structures. Going out a little bit further into our galaxy, we find this carbon spiral. Now, this area of space had been long known as a bright infrared spot, but optical telescopes showed nothing until Hubble did a long exposure, a 33-minute exposure. And it's just because this object is so faint that it took a long time for Hubble to gather enough photons. It's a binary system located about 3,000 light years away. And again, it has one of those great big red giant stars. And this one is particularly heavy in carbon. And this star orbits a smaller blue-white star, about 3 times Neptune's distance from the sun. So that's fairly close for 2 stars. And they take 800 years to go around each other. Now that red giant star is shedding material, which is mainly carbon, and carbon in space tends to form larger molecules, making a very fine black dust. And it's so thick around this star that it's actually blocking the light from that star. So we don't even see that star. Now, the other star is pulling this carbon off in its directions, and much of it would escape into space. And as these systems go around each other, the emitted dust is spraying outward, sort of like a spiral, like a water sprinkler. When it goes around, you can see kind of the spirals that come off of it.
Colleen, the carbon that ended up on Earth, is this how it would have formed within this type of dying star?
Exactly, yes, yes. Even our sun, as it goes through its evolution, will produce some carbon. So most stars do produce carbon that is shed off into the interstellar medium, where it gathers in clouds of hydrogen dust and then forms new star systems. Exactly right. So we can see that there's about 5 spirals. It's about 1/3 of a light year across, which is also quite small. So we have these spirals forming. Now, where else have we seen regularly spaced areas like this? Well, part of the Cat's Eye Nebula. So maybe the Cat's Eye Nebula, I should go back a bit just to refresh it. We can see these ejections here. This could very well be a binary star doing very similar things, ejecting this gas in kind of a water sprinkler method. Okay, let's go back to there. And now out into the universe. So the universe is made of galaxies. It's kind of the largest thing in the universe, and they come in only a few varieties. Nearly all galaxies are kind of called irregular or ball-shaped, kind of football-shaped galaxies. Or we can see irregular galaxies with just kind of a mishmash of dust and stars and gas. Or spiral galaxies like our own Milky Way. Now, spiral galaxies come in lots of different forms also, but they basically have this kind of main construction.
Is there a minimum size to be categorized as like a galaxy, or is there some kind of things that are kind of, they're just starting to form galaxies, so they're not quite big enough? Or
all galaxies were pretty much formed at the beginning of the universe, like 10 to 12 billion years ago. And it's their evolution that makes for the different ones. Galaxies like this huge elliptical probably has 1 trillion stars in it, probably resulted or possibly resulted from 2 spiral galaxies colliding and orbiting each other. These little irregular galaxies are all over the place, and they usually orbit other galaxies and slowly get devoured. Our Milky Way galaxy has devoured about 13 of these small galaxies. So there's more a progression towards evolution, but most of the galaxies were formed very early in the universe. So people were surprised. 1950, astronomer Arthur Hogue came upon a tiny faint ring surrounding a ball-like center, and of course reasonably firstly assumed that it was a planetary nebula. So in his telescope, which certainly isn't like any that we have now, not that high grade, he just saw a little central star and kind of a ring around it. Or it might be some kind of peculiar galaxy. He wasn't too sure. In 2002, Hubble showed that it is a perfect ring of stars, dust, and gas here, and a bright yellow nucleus. So it is a galaxy, but really unlike any that had ever been seen before. And it's really weird in that this nucleus sits all by itself in space, and 70,000 light years away is this ring of billions of stars and planets. So it is about 600 million light years away. So the inner core here is about 24,000 light years across, which is similar in size to the center of our Milky Way galaxy. And this outer ring is about 120,000 light years across. Our Milky Way galaxy is about 100,000 light years. So it's very similar in size, but it has this perfectly evacuated ring area here that, again, some hypotheses have been put forward, but nothing that explains it all. It's possible a smaller galaxy just hit it just right and went through and dragged some of the stars away, but there's no galaxy near it that could have acted like that. Or maybe spiral galaxies have an evolution or an unstable period that they can go through this type. Again, it's just not something we see anywhere else.
Is the nucleus the same as like the black hole at the center of our?
Well, there probably is a supermassive black hole right at the center.
Right.
And
Okay.
surrounded by millions of older stars.
Ah.
Yeah. So as unique as this one is, what would be the odds of, through that central part, seeing this object, which is another galaxy exactly like it? These might be the only two galaxies like this in the whole universe, and they just happen to be lined up. Truly unique. Excuse me. Looking at a supernova, and this one, supernova 2006, which means we saw it in 2006, inside a galaxy some 250 million light years away. Now, supernovas are the biggest explosions in the universe, but this one was 100 times brighter than any other that we have seen. It is so energetic that it has been named a hypernova. Now, I mentioned last week that there are different types of supernova. The type 1A is used in measuring distances out to billions of light years. This would have been a type 2 supernova, and that involves a single massive star that has completed all its fusion in the center. So the core doesn't have any pressure going out to hold the star up. The core collapses, the outer layers of the star crash down onto it, and it's that compressive forces that then create this huge explosion. Excuse me. Normally, type 2 supernovas, they will end up with, in their center, it might be a black hole, or it might be a neutron star. In this case, this object was so extremely rare in that the original star probably had a mass of 150 stars. Now that's near the upper limit where it's even possible to have a star. And even in our galaxy, we have 200 billion stars in our galaxy. stars that are this big number less than 10 in our whole galaxy. So they're very rare. And that's because they do not live long. The high temperatures and pressures that mass is pushing in at the core makes their nuclear fusion at the core almost a runaway. And they go supernova before they, between 1 and 10 million years. Now, our sun is going to last 10 billion years. These very, very large stars only last maybe 1 to 10 million years. So it's so massive that its output, and so the fusion at the center is so rapid that and has such intense gamma rays that there's actually matter antimatter pairs produced. When they contact, they release 100% of their combined mass as pure energy, and it produces this runaway reaction. And whereas these outer layers are funneling down into the collapsed core, the rate of the reaction, the temperatures, the pressures just skyrocket. And in this case, there is a supernova that leaves nothing behind. That original star core is blown to smithereens. At the moment of this explosion, it reached, the energy released was 10 million trillion times greater than our sun's total output. There, this energy output is so great. Here we have, looks like twins, whatever. This one is actually the galaxy that this hypernova lived in. And this is the hypernova exploding. So its light is equal to the light of 200 billion stars. And most supernovas do, their light output is brighter than the whole rest of the galaxy that they're in. There is a star in our Milky Way that may end its life like this. It's called Eta Carinae. It's the same kind of ultramassive star. It is 32,000 times closer to us than this star was, but when it explodes, and that could be tomorrow or that could be in a million years, it will appear about 1 billion times brighter than this one in our sky. But it's far enough away that it won't endanger anything on Earth, but it'll be easily seen in the daytime sky. So we're all hoping that this one will go supernova so we can see it. We haven't had a supernova in our Milky Way galaxy for about 400 years.
So the one, how long would we be able to see it for? Like, would it be like we talking days, months?
Well, we're talking months.
Yeah.
Several months.
And that's the process. That's how long it takes for the star to explode.
Yeah. Well, that's the energy finally dissipates. It takes months and months for the energy to dissipate as it expands into space.
Wow.
Yeah, that would be awesome to be able to see it. And we'd be able to see that one during the daytime, and at nighttime, it would be, just amazing too. So we're all hoping for it. So we all know that space can warp. And Albert Einstein's 1916 general theory of relativity predicted this, but he didn't think it would be observed. Now, remember, this was even before we knew there were other galaxies. So he was only thinking about the lens here being a star, and that would only show some weak lensing ability. And I forgot to mention what lenses are. So mass warps space, and light will follow the warped space.
Now, does mass warp space because of gravity?
Yes. We don't exactly know what gravity is. We don't exactly know how it acts, but we know that mass warps space because of the gravity. Anything with mass will warp space. So a fellow named Fritz Zwicky, he mathematically showed that a galaxy cluster, oh shoot, I meant to pull that up later. Anyway, he showed that a galaxy cluster could serve as a lens to focus the light of a bright distant star. So here we have Earth, here we have our lensing object, and here we have something far in the distant distance. So the light from this object will come out, and as it passes this object, which is warping space, it will bend. And we can then see it at different points in the sky. So here, if our galaxy cluster is fairly spherical, it'll produce an Einstein ring. So here we have the galaxy cluster in the middle, and this is actually the light from a far off distant object. If the galaxy cluster is more kind of oblong or egg shape, we get the Einstein cross. And if the galaxy cluster is there, it's very heavy, very massive, but it's kind of in blobs, then we get what's called lensing effects. And this is, so here we have a huge galaxy cluster, and here this blue streak and this blue streak and this blue streak. That's probably all the same galaxy that is far, far in the distance, but is being the light is being bent and stretched around the galaxy cluster. And I thought this one was appropriate for Halloween. Kind of looks kind of like a jack-o'-lantern. So what is the universe made of? So we have 2 trillion galaxies, each have an average of 200 billion stars, probably a trillion or so planets.
Wait. Well, what? Okay, okay, I'm up to speed. We got 1 trillion planets.
In each galaxy, yeah.
In each galaxy.
And 200 trillion galaxies.
And 200 trillion galaxies.
Or 2 trillion galaxies, sorry, 2 trillion galaxies. Was there a question?
No, we're just soaking that in. Someone was just talking about the nearest, the habitable zone planet in the nearest one that we learned about last week.
Yeah.
Anyway.
Yeah, even the newest estimates for our Milky Way galaxy is, I think it's 10 billion habitable planets. Or
10 billion, okay.
Earth-sized planets around sunlight stars in the habitable zone. The numbers are staggering. So we have 2 trillion galaxies, 200 billion stars in each one, 1 trillion planets in each one. All that stuff we can see and that we understand the physics of it mostly, makes up only 4% of the whole universe.
Wow.
And most of that is hydrogen gas between galaxies. So about 4%, most of it, the hydrogen and the helium. Stars make up a little bit, neutrinos make up, and all the heavy elements, which would include all the planets and all of us, is less than 0.03% of the total universe. The rest of the universe is made out of 2 things that we are calling dark matter and dark energy, partly because we are in the dark. Dark matter is called matter because it acts gravitationally on the stuff we can see. And in this case, the matter, it can also be called dark because it doesn't react at all with the electromagnetic spectrum. It doesn't absorb light and it doesn't emit any light, so we cannot see it. But we know it's there because we see its effect on the stuff that we can see, like the galaxies in their rotation rates and there's the way they go through space. We know that there's at least 6 times this dark matter than normal matter. Excuse me, I got a really dry throat this morning. And the rest of the universe, about 74%, is made out of dark energy. And in this case, dark means we have no idea what we're talking about. We know it's there because we see its action on those galaxies also. So 2 trillion galaxies, and they're all moving away from each other at an accelerated pace. So they're moving away from each other faster and faster. That takes an enormous amount of energy, equivalent to 74% of the whole universe. And we've only known this dark energy for about 25 years that it exists. So we're really in the infancy of studying it. But nothing has explained anything yet. So these are two things in the universe that we really do not have a good hold of at all.
And are these two things, they're widely accepted that these are both types of things that are out there?
Yeah.
And I guess the scientific community is now looking at how to figure out what they are.
Exactly. Well, it's basic physics that shows us that this stuff is there. And the search for dark matter is really trying to gear up. But every type of dark matter that we have thought about, we have not been able to see yet. The Large Hadron Collider over in Europe may, within the next couple of years, be able to produce a dark matter molecule or whatever it's made out of. So it's matter that works gravitationally, so it interacts with space-time, but it doesn't interact with matter.
Right. So one of our students is reading the Da Vinci Code right now.
Oh, yeah. I like science instead of... Sorry. So I want to end with one of the weirdest things that I think in the universe, and that's time dilation, length contraction. There's math involved, but you don't have to look at it. The only part of these equations I want you to look at is this part. So v squared, which would be your velocity over c squared, the speed of light squared. And that's in both of these equations. So it's the ratio of how fast you are accelerating compared to the speed of light that will determine your speed of time. That's not a good way to put it. Your time and how big the universe is. So if we start going through this really slowly, if you're going at 10% the speed of light, which is really we can might see that eventually being able to happen. What that does is increase your time by just this little tiny second. So so when someone's on Earth and you're speeding away at 10% the speed of light, every 1 second that you experience, the person on Earth will experience just a little over 1 second. At 50% the speed of light, it's the person on Earth just 1.1 second. We can see as we get closer to the speed of light, 90%, we're up to 2 seconds, 95 up to 3, 99 up to 7. At 99.9% of speed of light, your 1 second would mean 40 seconds for the person on Earth. If you think of it the other way, they would see your time as slowing down. You feel the same time that you would before, but because it's relative to the speed that you're going, that's what gives us time dilation. If we look at 100% c, so if we put this velocity equal to c, this whole equation turns into 0. At the speed of light, there is no time. To make that match, to work that out, there's also a length contraction as you move through space.
Wait. So at the speed of light, there's no time.
There is no time. Yeah. Yeah, I know. Same thing happens to length.
Well, how do you know, like, when if you can go the speed of light and then you want to stop? I don't know. Okay,
just wait. Just wait. So again, same thing happens with length or distance. 1 meter on Earth, if you're going 10% the speed of light, would mean you would only have 0.995 of a meter. And we can see this meter length gets shorter and shorter and shorter until at 100% the speed of light, there is no universe. Your length is 0. So this might be an easier way to look at it through a graph. So here we have time when we're going really slowly compared with the speed of light. Our times are pretty much the same.
Good times.
As we get closer and closer, our times lengthen. Our times slow down for us. The person traveling at that speed, the time slows down, although they don't realize it. This is actually like a 4-year course, so I'm really trying to condense it. Just believe me that the closer you get to the speed of light, the slower your time appears to others.
So if you could travel around everywhere at the speed of light, you could theoretically live forever.
Well, let's just hold on a moment.
No, because your body's still going to age.
And for length, if we're going slow compared to the speed of light, our lengths are pretty much the same. But as we go faster and faster, our lengths shorten. And as we get to the speed of light, there is no length. What this all means, so that's at the speed of light, there is no time or space. Is there anything, well, I kind of answered the question. So our universe has a speed limit, and the only thing that can go that speed limit is light. It cannot, when light is produced, it doesn't, speed up to the speed of light. It is, as soon as it's produced, it instantly is at the speed of light. It cannot go any different speed. So if we have no time or space with something going the speed of light, that means that photons know no time or space. We see light moving at 300,000 kilometers a second. The photon that is doing that has been created and destroyed instantaneously, because for a photon, there is no time and no space. That to me is the weirdest thing about this universe. And, so happy Halloween, everyone. This is the sun. Kind of looks like a jack-o'-lantern to me. So I'm glad I've blown all your minds, and happy Halloween.
Happy Halloween.
So are there any questions?
Any questions, gang? Oh, we got a question over here from Casey.
So if you were traveling at the speed of light for 80 years,
Okay.
come back, would everyone else be the same age? And you would just die of age? Well,
I didn't hear your whole question, but I think I know what you meant. So if you leave Earth traveling very close to the speed of light and then turn around and come back, the Earth is going to have aged possibly millions of years. You might have only spent 20 or so years going out and back. There are calculations that you can do, but yeah, the people, if you're traveling very close to the speed of light, time moves slower for you. So the people back on Earth will have aged greatly.
And I have another. So is there an end to the universe? where there's no more planets and stars?
Is there an end to the universe? Is that what the question was?
Yeah, he said, is there a spot where there's no more planets and stars?
No. Basically, no. So all those galaxies far being flung apart, if we turn that movie backwards, we can see that at one point, about 14 billion years ago, everything was in one spot. And the Big Bang happened, creating space and time. So everything we see is within our universe, is within our space-time bubble. Now, we figure the universe is actually about 93 billion light years across, of which we can only see about 14 billion light years out, because that's how long the universe has been around. So that's how far light could have traveled during that time. There is no space where there is nothing. Like it does, the universe, the planets, the galaxies, they don't end and then there's nothing. The whole universe is filled with stuff.
Cool. Any other questions? Oh.
So what you were explaining is that light knows no time and knows no distance.
Right.
So based on that, considering that our base unit of measurement for this sort of scale is light years, that's time, and that's a distance. So wouldn't that be just not the best way of measuring something?
No, it's not. And
If the thing that you're using to measure it knows neither of them.
but we are doing the measuring, so we can do that. Real astronomers don't use light years at all. They use something called parsecs, or parallax seconds. It's a direct measurement using trigonometry. The public generally use light years because it also gives us an idea. If we say something is 2 million light years away, we know that means that we are seeing that object as it was 2 million years ago. So that's why the public generally uses light years, because we can relate it to time. And so we see nothing as it is, everything is as it was. But real astronomers use actual measurements of parallax.
And does that have its own units of measurements, its own scale?
Yeah, I went over that a little bit last week.
Right.
For parallax, putting your finger out, looking left eye, right eye kind of thing. If you use that, you actually, it's a trigonometric function. So it's called the parallax second being an angular thing. So that's been shortened to parsec. So parsec is a measurement of distance. If you've watched Star Wars and Han Solo says he made the Kessel Run in 12 parsecs, that means absolutely